We are from Group 1, and the member is Justin Dewanga, Prasnaria Bimo, Ryan Josia, Jun Sustanya, and Ko Ferdinand. Today we will presentation about the final exam MSD. Over 8 meter, a pick and place robot need to carry up a cup of water from one point to another with minimal spillage and maximum dish. This problem was given as the main task to solve during the MSD1 course. To do this, there are various design objectives and constraints we must follow. The robot must be as fast as possible, however, must be stable not to keep the water cup from spilling. The pick and place system needs to be able to take the water cup from a platform but must not be held into the water cup on the robot itself. The entire robot must be sturdy enough to withstand sick tests. With that being said, the most important part of this text was the speed and stability of the robot. Knowing that the final criteria will target these two aspects, the robot will be created with these two objectives.
So overall, when the power supply is turned on, the system on the robot will be on and in standby mode. When button 1 is pressed, Arduino Uno as the master will send commands to Arduino Nano as a slave to take a glass of water to the robot platform. When finished, Nano will give Uno a feedback and the robot will bring the glass to the target point 8 meters away. After that, Uno will give another order to Nano to take a glass of water from the robot and place it at the target location. Then, just like before, Nano gives feedback, the robot will return to its starting position and then return to standby. So for the deceleration process, we make sure that the integral part of the PID is used only when it is close to the target, so it won't overshoot too much. And to get a better result, we also reset the integrals every time it reaches the goal or it reaches the limit speed when the robot is very close to the goal. Here is the isometric top-below view of our robot design. Here is the front, back, left, and right view. So in design calculation, we made at the beginning of the course. Since this is at the beginning of the project, everything here is based on assumptions. With those assumptions, we get the maximum speed, and then assuming the time to reach the maximum speed is 0.8 seconds, we are able to get the acceleration. And from the acceleration and rolling resistance, we are able to get the force needed at the wheel, also the torque at the wheel. Calculating the angular speed of the wheel, we are also able to get the power needed for the motor. And with gears ratio known, we can find the RPM at the motor. From all of the specifications we got, we can compare it with the specification of the motor and input them to the torque versus speed graph, and they are still inside the parameters, which is good. Here's the calculation for the encoder. We use a library to read the encoder pulses. The library uses two interrupts for pin A and pin B. The interrupt surface routine will be called whenever either pin changes, both rising and falling. So the library will read 4 times the original encoder pulse. And the ISR will also check the state of pin A and B to see the direction of the rotation. And from the resolution of the encoder, also the circumference of our wheel, we get around 0.18979 mm per pulse. And still assuming that is an ideal condition, the error will occur will be only 0.00035%. So for the robot arm calculation, we use a simple calculations that uses moment force. So here we choose MG995 servo that is able to give an output torque of 10 kg/cm for around 5 to 6 volt supply. Calculating the capability, the servo is able to hold a mass of 0.833 kg that is placed for distance of 12 cm, so it should be enough. And here is the arm robot that has the length of 24 cm. We calculate the capability of the MG995 servo again, and it seems still be enough to hold 0.25 kg mass, but since nothing is ideal in the real world, to make it safe, we also added a 20 kg/cm torque servo.
Okay, next we will talk about the fabricated parts. These are the parts that we fabricated. The whole arm is actually fabricated from 3D printed parts and some acrylic. It's not a good idea to 3D print everything, but we did it. And the most important part are the gears for the motor to the shaft, the mobile base, and the arm, of course. This is some of our expenses on the fabricated parts. There are some bot parts like the rotary encoder and the Aki, but roughly the fabricated parts cost us about 500,000 rupiah each. Next, these are the mechanical designs that we use in the mobile base. For the drive, we used a gear, so it have enough torque to push itself. And for the pulley system, we just use 1:1 ratio for the encoder.
And here is our electrical wiring diagram, where we have several components that is listed at the left. And here is our flowchart of our programming. So as we can see here, when the system has started, there will be an independent button that is used only for adding 1 to the state. While we can see next to the button there is a branch that explains what is the state is for. For state 0, the robot is in rest or stop condition. So when the button is pushed, the state will change to 1. And if the state is equal to 1, the master will send the current state 1 to the slave, and the slave will read it as an x variable. And if x is equal to 1, a run variable will also be equal to 1. And an input of x, y, z will be given to the inverse kinematics equation for the robot arm. If the robot arm haven't made to its target point, it will keep sending the input x, y, z and calculate the inverse kinematics. But if the arm robot has reached the target, which taking the cup and place it to the robot platform, a variable y will be equal to 1, and the slave will send the y value to the master. If the master read the y to be equal to 1, then state will be added by 1, which will then continue to state equal by 2. So if the state is equal to 2, it will go to the part where the robot take the glass of water to the goal position 8 meters away, where it starts from reading the encoder, set the target goal which in number of pulses, set the range for tolerances in calculations, and continue with the PID calculation which controls the motor speed. If the robot haven't reached the target goal, then it will keep looping until it has reached the target goal, and then state will be added by 1 again. So for the rest, it will be similar to the previous, but the difference are the arm robot will take the glass of water and put it on the target's goal platform, and then the robot will go back home, and the state will be reset to 0 again. So looking at here, we have actually added a separated special feature on our robot, which we can customize for our robot arm to move independently from the system drive. And here is the inverse kinematics function that we have studied and integrate from many kinds of sources. And this equation suits us best. As for here is the important equations needed for the PID control calculations.
The results and discussion. So for test 1, as you can see from the results on screen, the timing is fairly consistent. However, there is one major outlier in round 4 going backwards. As you can see, there is a much larger time at 46.43 seconds. Now the reason why this is because the robot, once reaching its final position, had actually began oscillating back and forth. And this oscillation caused the time to be a lot longer. And in the end, it took around 46.43. However, if we're only counting the fact that it reached its final position, it should only be around 13.88 seconds. As you can see from the placement results, it's also fairly consistent. It's constantly undershooting. However, it's only undershooting by about 2.5 to 0.5 centimeters. Okay, so what did we learn from this test? So here we learned that we need to move the encoder to the front of the shaft because this reduces the amount of slippage and has independence from the motor. So the motor shaft was actually the shaft that was causing a lot of the slippage, and if we move the encoder to the front shaft, this could mitigate a lot of the issues. We also found out that the tiles in the room could be causing the jumps in the encoder. As mentioned before, when the robot was oscillating back and forth, this was caused to it running over a divot in the floor and causing the encoder to jump in values. So we have to be careful for that. And all of this culminated in test 2, where we also added a new motor, which made the runs a lot faster, as you can see from the result. Testing here was not mainly about the speed of the robot, but mainly about how it affected the robot in terms of how it needed to be changed. So for example, A new motor meant we had a faster robot, and a faster robot meant we had more slippage, therefore we had to change the PID. However, that moving the encoder to the front helped to mitigate a lot of the issues that we had, and it also helped make the robot a lot more accurate. So we learned that the robot can run at a much faster pace so long as the PID is adjusted to match said pace. So long as everything is balanced, it's all fine. So final testing for the shake test. As you can see, nothing really went wrong with the shake test. We had multiple times to test our robot, and we found that the arm was the weakest link, so essentially we just anchored it down even stronger so that in the final testing and the final runs, it would be completely fine. For the delivery, we had some issues with some skewing. Every single time the robot would run forward, it would always slightly move to the left, and it even caused the robot to crash into the platform once, causing a little bit of spillage. As you can see here, from one of the cups that we measured, a little bit of spillage was caused by the crashing into the into the platform, causing about 1 gram of accumulated spillage. Other than that, the delivery was completely fine in terms of putting the cup onto the platform. Now let's talk about the final results. As you can see from the 5-minute runs, our robot was able to deliver 7 cups of glass, and each of the weight of the glass from the starting weight to the final weight, as well as the error in centimeters, was also recorded. Now let's look at some graphs for a more visual representation of our data. So as you can see here, the placement accuracy is fairly accurate, only having a maximum error of around 2 centimeters. You can see that the standard deviation is 0.69, and on 3 rounds, it even managed to have a perfect placement in the middle at rounds 3, 5, and 7. For the difference in water weight, as you can see, there's a major outlier in round number 3. This is due to the fact that in round number 3, a screw actually got stuck on one of the wheels and caused a lot more oscillation than was intended. Other than that, if we don't count the outlier, we can see that it is fairly accurate in terms of the fact that it only dropped about 1 gram of weight on 3 runs, and even managed the exact same weight on 3 runs as well at 4, 5, and 7. Now for the shake test, due to the anchoring that we had installed, the shake test for the final day was actually very good. Nothing fell off and the robot remained really sturdy. Everything on the board remained in place, and everything is fine. In terms of improvements that we could possibly make, there will probably be minor ones, such as making the arm out of a stronger material in order to make it not oscillate as much. But other than that, everything's fine. So now let's talk about the main point of error. So the arm sags quite frequently, and if we had more time and more resources, we would build the arm out of a stronger material in order to mitigate this sagness. Of course, we mitigated it in using the servos to lift the arm slightly up. However, if we wanted a more true sturdiness, we would make it out of a better material. The left skewing could have been caused by misalignment of the wheels or probably the shaft. And in order to mitigate this, if we had more time and more resources, we would build it out. We would build a contraption or some sort of mechanism to help correct this, such as maybe a steering function, self-alignment function to help align the wheels better so that it was straight. So were the results as expected? So in the end, the results were as expected, but how we got to the results was very different. Changes were made over time, which completely changed the final result from the initial calculation. So for example, speed changes had to be made. We intended the robot to only run at around less than 1 meter per second. However, due to the faster motor, of course, this had to change the speed curve and everything like that. Real world factors also had to be taken into account. For example, the gear backlash caused by the 3D printed gears, as well as the floor tiles and the uneven floor, all caused some changes to the expectation. However, the final result was as expected. We have screenshots of the output for one of the runs. As you can see, home ticks is 0 and goal ticks is 42,214. The robot picks up the cup and then starts moving at around 7 seconds. It then accelerates for about 2 seconds before reaching constant speed and remaining at constant speed for about a second. Once it's there, it then begins to decelerate after about a second, and then it reaches its final position after about 15 seconds for the run. After this, as you can see, it actually overshoots the final goal and has to correct itself, causing for a bit of lost time. The whole run then ends up going at about 37 seconds. In an ideal world, it would only be about 30 seconds. However, due to real-life factors, it would some lost time had to be made up for by correcting. Of course, this caused the entire run to be a lot slower than what was expected. However, in terms of the placement and the ability and the function of the robot to put the cup where it's intended, those were all as expected. So what causes these consistent errors? So, for example, the constant skewing to the left is probably caused by misalignment of the wheels and imprecise wheel placement. And then the overshooting of the robot was probably caused by real-life factors such as slippage, as well as the friction of the floor and so on. In terms of the arm, there were no real errors there. However, if we count the arm sagging as an error, it's probably caused by the materials. Other than that, there were no real other errors that we could really account for.
Next, we have the design lesson that we learned from this project. The last-minute designs are the top arm stabilizer and the anti-spill acrylic. The arm stabilizer is to minimize the sagging of the arm, and the anti-spill acrylic is a precaution if there were any spill. During the test, we had a little problem where a lead screw got stuck on our wheel and made the robot spill some water. We could have prevented this by cleaning the floor before testing, or if we have any time and money, implemented a suspension system. The hardest part to manufacture is the baseboard because we had to manually drill the holes, and because of that, they were not accurate. The solution to this problem is just to use a CNC router to make the holes. Next, the hardest assembly on our robot is the arm, because the whole arm is made out of 3D printed parts. The solution to this problem is simple. It's just to make a new design that has less part than it needs. Next, the least reliable part are the wire connectors. If you nudge it a bit, it will disconnect and connect again. The solution to this is just to solder it into the PCB. The parts that are not suited for repeatability is the wheel and the shaft due to their inaccuracy. To fix this, we need to buy new wheels and have a more accurate pillow block placement. And last, our LCD and button can be improved for user friendliness. The LCD should display more information and the button should have a label that says start.
So for a special feature that lies on our robot is its overall rigidity and strength. We have survived vibration tests 3 times a row without having any casualties and reparations. Even though others has their own strength or has the most standard robot for this project, our robot weighs about 9.4 kg, which is not that heavy. Even though our arm is complex, it has done its job perfectly, and the space consumption is relatively small with the strength ratio, and it looks cool. Our electrical wiring is straightforward with the labels on the important parts, so it is easy for people to understand. And the most important part, even though this does not relate to the project, our robot has a special feature that no one has. We made our arm robot to has shake function, so we can test its reliability, and we can also make custom actions for the arm independently with the system drive, so we can use it anytime and everywhere the robot is.
So for the lessons learned in the design process, prototyping and testing, we could have done more iterations to design. We could have made a more consistent prototype because some of our prototypes are kind of unstable, and we should test it more times, around 5 to 10, and then change over to the programming and mechanical aspects. As for the lessons learned, we could have developed a more detailed plan which we could improve since some of the situations didn't actually go as planned. We could have divided the work more equally. So we weren't able to divide the work more equally until the last week remaining. This also adds to time management. We think we done pretty well compared to other groups, but as we did a minimum of 30 hours per week, but there was also weeks that weren't very productive. Here's the code, and here's the list of the components bought. Here's the specification of the rotary encoder. Here's the specification of the motor. Here's the specification of the servo. 1, 2, 3. Here's the technical drawing of the gears that we used. And here's some pictures of our robot. Thank you.
Oh my god.